All right, let's get right into it. NVIDIA just dropped something called Jet-Nemotron, and the numbers they're claiming are, well, they're pretty wild. We're not talking about some small incremental improvement here. This looks like a complete rethink of how we build large language models, with a laser focused on efficiency. So, of course, the engineer in me is asking one thing: how on earth did they do it?
Yeah, that's the number that's got everyone talking. A 53.6 times increase in generation throughput. Now, when you see a number like that, you know it's not just a clever software trick. That signals a genuine breakthrough, a solution to a really deep fundamental bottleneck. So the question isn't just what they did, but how they architected a system to get this kind of speed up without torpedoing accuracy. Let's break down the engineering.
So, here's our game plan. We'll start with the scaling problem we all know and love. Then we'll look at the clever hybrid architecture they came up with to solve it. After that, we'll dive into the actual benchmarks and, finally, talk about why this could seriously change the game for all of us.
Okay, Section 1. Let's be honest, we've all felt this pain. The transformer architecture is amazing, but that core self-attention mechanism, it's also its biggest weakness. It's Achilles' heel, especially as we keep pushing for longer and longer context windows.
This right here, is the fundamental tug-of-war in our field. On the left, you've got standard attention. It's powerful, it's expressive, but it has that O of n squared quadratic complexity. You double the context, you quadruple the cost. It's just brutal. On the right, that's the dream, right? Linear attention, O of n, predictable, efficient scaling. The entire industry has been trying to get the performance of the thing on the left with the efficiency of the thing on the right.
And here's the real culprit. It's not just about raw compute. It's a memory problem, specifically the key value cache. You know the deal. We cache these intermediate states so we don't have to recalculate the entire context for every single new token. But as that context gets massive, the cache just explodes in size. We become totally bound by memory bandwidth, literally how fast we can move data on and off the chip. This cache is the villain of our story.
So if the KV cache is the villain, how do you defeat it? Well, the answer comes from challenging a really basic assumption we've had for years, that every single layer in a transformer needs to be the same heavyweight full attention layer. Turns out, that might not be true. NVIDIA's team did a ton of ablation studies, basically carefully taking a model apart piece by piece, and they discovered three really crucial things. First, for the really hard reasoning benchmarks, you only need a handful of those full attention layers to do the heavy lifting. Second, which layers matter most actually changes depending on what you're asking the model to do. And third, the layers that are crucial for basic reasoning often happen to be the same ones you need for more complex stuff like math. This is the evidence that justifies a more surgical, hybrid approach.
And this quote just perfectly captures the shift in thinking. For years, the mantra has just been scaling laws. Throw more data, throw more parameters, make the model bigger. This work suggests a different path forward. That smart, architectural choices, designed hand-in-hand with the hardware in mind, is the next big frontier. It's a move away from pure brute force and towards real engineering elegance.
So how did they actually build this smarter architecture? It really comes down to two key pieces of engineering, a process they call PostNAS and a new component they built called JetBlock. PostNAS is it's incredibly clever from a cost perspective. Instead of training a whole new model from scratch, which costs a fortune, it's a retrofitting process. You take a powerful, pre-trained model, you freeze its MLP weights to keep all that amazing knowledge it's already learned, and then you perform precision surgery on just the attention layers. It makes exploring new architectures vastly cheaper. And the process is super methodical. Step 1, figure out the absolute minimum number of full attention layers you can get away with. Step 2, search for the best off-the-shelf linear attention blocks to replace all the ones you just ripped out. Step 3, take what you learned and design a brand new, even better block. And that's how JetBlock was born. And then step 4, and this is so critical, a hardware-aware search that optimizes everything directly for throughput on a real GPU, like an H100, not some abstract academic metric. So this is the result of that process. JetBlock. It's a new linear attention module. The cool part is that it uses dynamic convolutions on the value tokens, meaning the layer can adapt to the input it's seeing. But the really efficient part is that they completely cut out redundant operations on the query and key tokens that older designs used. They found those operations were adding a lot of compute for almost zero gain in accuracy. So, snip, they're gone. Okay, so the theory is elegant, the engineering is smart, but does it actually work in practice? As we all know, the proof is in the performance. So let's look at the numbers. And here it is. This is the smoking gun. This is the root cause of that massive speed up. Look at the KV cache size at a 64,000 token context. A standard model needs over 7 gigabytes of VRAM just for the cache. Jet-Nemotron, 154 megs. That is a 47x reduction. It's not an improvement, it's a whole different category. You're just moving so much less data around.
And that 47x drop in cache size translates directly into this. A 47x increase in throughput. You go from a sluggish 61 tokens a second to almost 2,900. When you remove that memory bottleneck, your compute cores can finally stop waiting around and just run.
This table really tells the whole story. Look at Jet-Nemotron 2B. It actually beats the full attention Qwen 3 model on accuracy. Now look at its speed. It's right up there with a pure linear model like Mamba 2, which, well, look at Mamba 2's accuracy. It's not even close. This is the holy grail. They've managed to get the accuracy of a full attention model with the raw speed and efficiency of a linear one. They broke the trade-off.
And this isn't some magic that only works in a giant data center. These efficiency gains carry over. You're seeing an almost 9x speedup on an edge device like a Jetson Orin, and a 6.5x speedup on a consumer RTX 3090. This is the kind of engineering that unlocks powerful AI on robots, in cars, or just running on your local workstation.
So, let's zoom out. What does this all really mean? Because the implications here are much bigger than just one fast model. This number right here, it represents a potential 98% reduction in the cost of inference at scale. And when you make something 50 times more efficient, you completely change the economics. Use cases that were just way too expensive to even consider before, suddenly they're on the table. This opens up entirely new markets.
And honestly, work like this should force all of us to change how we measure and talk about models. For too long, parameter count has been the lazy, default metric for how good a model is. Jet-Nemotron proves we need to be looking at things that actually matter for deployment. Real-world throughput, tokens per dollar, KV cache size, and performance on the specific hardware you're targeting.
And maybe the best part of all, for everyone in the community, they've open-sourced the key components. The PostNAS method and the JetBlock module are out there on GitHub. This means anyone can now take this retrofitting approach and apply it to other great open-source models. It really democratizes this kind of high-level architectural innovation.
Which leaves us with this final thought. For the last few years, progress in AI has felt like it was defined by one thing: scaling laws. Bigger models, bigger data. Jet-Nemotron makes a really compelling argument that the next great leaps in performance might not come from brute force alone, but from intelligent, hardware-aware architectural design. And that's a question that could define the next chapter for all of us.